Hey guys, it's Mrs. Wallace. I hope all is okay and you guys had a restful break and everybody in your family's doing a-okay. It has been a little bit wild and you know and I know, so we'll just kind of hold on to some of the things that we've got going on. And just a reminder, the AP exam will be in May. It'll be something you can do online. Whether we're back in school or not, and it'll be about 45 minutes long, and we'll be on May 20th, so I'll be updating you a little bit more about that so you have an idea. But remember that we're looking at the fourth of our markets, so we've had monopoly, perfect competition, monopolistic competition, and now oligopoly. Oligopoly is a fairly concentrated industry, usually a few big players. You might have a variety of different models with oligopoly, so it's not uncommon to see a variety of different types of graphs for oligopoly. For example, you might have oligopolies that collude together and basically tag team and kind of create a monopoly, and they graph very similarly to a monopoly. We might also see oligopolists that are largely competing, and in a lot of cases we will recognize that oligopolists are interdependent of each other, and because of that we tend to see a lot of game theory. Every decision that one player in an oligopoly makes is dependent on the other player. So the two practice questions that you guys had before break, you had two examples, and I just wanted to note them because there were a couple of different questions. One was the example a prisoner's dilemma? Was the example, what was the Nash Equilibrium? And did either player, have a dominant strategy? So let's look at our two examples. This should be a short video, but it was the second of the two examples that was perhaps most confusing because it was clearly not a prisoner's dilemma and was also not a, was a situation in which there was a Nash equilibrium, and a couple of you said that there was not. So make sure you look at the second problem as well as this one. This is the Coke versus Pepsi, kind of very typical game theory example. So let's look at this one first. In this case, and just a reminder, we have two players. We have Coke and we have Pepsi. Both of the players have payoffs that are in the board, and both players have a decision to make. They're going to either advertise or not advertise. Okay, so regardless of whether you're Coke or you're Pepsi, those are your two choices. Okay, and in the situation where Coke does advertise, if Pepsi is making the decision and knows that Coke will advertise, Pepsi has a choice. They can either advertise or not advertise. What would be better? Of course, the better choice for Coke would be to advertise, and so they would advertise versus not advertise as long as Coke advertises. If Coke, of course, decides not to advertise, and kind of looking here, then the two payoffs that Pepsi would be choosing from would either be to advertise or not advertise. So in this case also, Pepsi would be in a position to definitely advertise. Okay, so regardless of whether or not Coke advertises or doesn't advertise, the best response for Pepsi is to advertise. And because we know that their best response, regardless of what Coke does, is to advertise, we will definitely say that Pepsi has a dominant strategy, and that dominant strategy is to advertise. No matter what Coke does, Pepsi's always better off advertising. Okay, let's see what's happening with Coke's decision making. If Pepsi was to advertise and Coke knew that Pepsi was going to be advertising, Coke, whose payoffs are in red here, could either advertise or not advertise. Okay, so the higher payoff for them, of course, is to advertise. If they decided to advertise, then here we are, they would decide to advertise. If Coke knew that Pepsi was not going to advertise, they could either advertise or not advertise. The better payoff for them, of course, is to advertise. Okay, so in the case of Coca-Cola, regardless of what Pepsi does, Coke is always better off advertising. We do know that if both players have a dominant strategy, and the dominant strategy for Coke is to advertise, and the dominant strategy for Pepsi is also to advertise. Both players, if they're playing a simultaneous one-time game, will advertise. It's their dominant strategy. It's their dominant strategy because regardless of what the other player will do, both will advertise. When both advertise, we're going to have each player playing their best response, and we'll call the cell in the payoff matrix wherever the two players are playing their best response will be a Nash equilibrium. And it's very possible in some games there can be more than one Nash equilibrium. In this case, we are going to note this as a classic prisoner's dilemma. Okay, what are the things that make it a classic prisoner's dilemma? First of all, there are two players, and both players have a dominant strategy. The dominant strategy is to advertise. Okay, so in order to have a prisoner's dilemma, both players need to have a dominant strategy. Furthermore, when the two players actually go and play that dominant strategy, they do get a Nash equilibria. When both players are playing their best response, we have a Nash equilibrium. In this case, advertise, and I know it's a Nash equilibrium because no player will deviate elsewhere. Okay, the 80 that Pepsi will get from advertising, as long as Coke is advertising, they're not going to deviate and choose 45. And the same thing with Coke, right? If Pepsi is going to advertise, Coke is either going to get 80 or 45. It's not going to deviate, okay? So this is a stable Nash equilibrium. We know it's a Nash because no one has an incentive to choose their alternative choice. Both players are playing their best response. The problem with a prisoner's dilemma is that the Nash equilibrium, in this case 80 and 80, let's say $80 million and $80 million if both Coke and Pepsi advertise at the same time, is not Pareto optimal, okay? Both are advertising and likely they're canceling each other out. Advertising is fairly expensive and both are advertising at exactly the same time. It's not necessarily the most optimal decision. If they could actually communicate ahead of time and collude and pick a payoff matrix on the board, they would pick the Pareto optimal cell. They would pick 100 million and 100 million. Okay, let's say that this is in millions. So in that case, this would be the Pareto optimal. And the prisoner's dilemma, the dilemma is the incentives are kind of pushing this Nash equilibrium, but it is not Pareto optimal. Okay, so if you have a situation such as that, where two players playing their dominant strategies leads to a Nash equilibrium, but the Nash equilibrium is not Pareto optimal, in that case, you have a prisoner's dilemma. Okay, let's take a look at this one. This one was a little bit trickier because in this case, we have to see what's happening with dominant strategies. So we have ace current, which is in green, and we have river queen, and both of these are producing canoes, and they're trying to decide, should they produce the regular canoe or should they produce the premium canoe? These are our payoff matrix. This is the payoff matrix. Each of the cells show different degrees of profit that they will get from either type of canoe. And of course, if river queen does a premium canoe and ace current also does a premium canoe, the situation is different than it would be if river queen, say, did a regular canoe and ace current did a premium canoe. Okay, so we can kind of look at this from the perspective of each one. I tend to like to start with the player on the left, and just a reminder, the player on the left has the left-hand part of the payoff matrix. And it's very possible that you might see diagonal lines kind of splitting the two payoffs. It doesn't really matter if it's a comma or whichever. Always the one that's most on the left is going to be for the player that's on the left, okay? And you can kind of use a pen to suggest where you might see a best response, and it'll help you figure out a dominant strategy, or if not, at least a best response. So let's look first at river queen. River queen is going to consider, what if ace current goes premium? Okay, if ace current goes premium, river queen has two choices. Okay, they can either go premium as well, or they can go regular, right? They will decide to go premium because 400 is higher than 150. If they know that ace current is going to go regular, and we assume that both players know the payoffs in advance, if we know that ace current is going to go regular, what should river queen do? Okay, they could either choose 450 or 200. Those are their two choices. They are going to choose 450. So in the case of river queen River Queen has a dominant strategy. River Queen should always go premium. The reason they should always go premium is because regardless of what Ace Current does, they should go premium. Now, if we look at things from the perspective is if you were Ace Current, and Ace Current has to consider things. What matters is what River Queen will do, okay? So if River Queen were to go premium, okay, then Ace Current can either do 100 or 200. They would pick regular. They would do 200. If River Queen goes regular, okay, then Ace Current can either do 400 or 150, and they would choose 400. In this case, notice that there is not a dominant strategy for Ace Current, okay? If River Queen does premium, they should do, they should do 200. If River Queen does regular, they should do 400. So it depends on what River Queen does. In this case, however, we can still figure out what the Nash equilibrium is. Notice that each player, there is a best response here that is shared, okay? In this cell, this is only a best response for River Queen. In this cell, the 400 is only a best response for Ace Current. But in this cell here, this is definitely a Nash equilibrium because it is the best response for both Ace Current and for River Queen. And that should make sense because River Queen has a dominant strategy. We know that River Queen should go premium regardless of what Ace Current does. So if River Queen goes premium and is going to pick that 450, we know that Ace Current, if they know that River Queen will definitely go premium, then they're only interested in making a choice between 200 and this 100 over here. They'll choose the 200. When both players play this game simultaneously, knowing what each other will choose, this will be the Nash equilibrium. And you can always check a Nash equilibrium, right? You can decide, is say Ace Current going to switch? Do they have an incentive to switch to the 150? No, they have no incentive to move from this Nash equilibrium. If we had a situation like here that River Queen is at 450, do they have any incentive to move to 400? No. So this is a stable Nash equilibrium, okay? And as long as it's a one-time game, this is where these two players will continually end up. This is what the incentives suggest, okay? This, of course, is not a prisoner's dilemma, okay? First of all, both players do not have dominant strategies. And even though there is a Nash equilibrium, we don't have a situation where the Nash equilibrium is not Pareto optimal. In fact, if they were going to collude and pick the best cell in the payoff matrix, this is likely where they might pick, right? I mean, there'd be some debate about that because perhaps this player could be much better off here. But in any case, it is not a prisoner's dilemma because the Nash equilibrium is not pulling us into something which is clearly worse and not Pareto optimal. Okie doke, I hope that helps. Have a good rest of the day.